Welcome to Math 31. This is a continuation of Lesson 2. We will be working with critical numbers, as in the Part A, but now we're going to be doing first derivative analysis on these critical numbers. What this will allow us to do is identify whether these critical numbers are minimum values or maximum values. Should point out that the very first lesson we did in this unit was basically that, the first derivative analysis. So really all we're doing now is adding a few little details to it, and then actually in a few of the examples we'll put them up on a graph. We'll sketch them and see if we can make some sense of it. So it isn't really a big step forward, but it adds a few more details that you have to be very, very aware of. So first derivative analysis for critical numbers on a continuous function. First point is if the derivative changes from a negative value to a positive value at a critical point or a critical number, then the critical point or number is a local minimum. So I addressed that earlier, and it does make sense because the derivative is telling you the direction, or the sign of the derivative is telling you the direction of the slope of the tangent line. And then conversely, if it changes from a positive value to a negative value at this critical point, then the critical point would be a local maximum. And remember, none of these give you information about absolute mins or max, just the local, what's happening in that vicinity. If it's a complicated graph, you might have several local minima or local maxima. And then the other thing is, if the sign does not change at a critical point where the derivative is equal to 0, then the critical point is a horizontal point of inflection. And in the future, points of inflection we'll call POI, just to keep it a little simpler. So we've been here before. Really, this last bullet just addresses what we saw on that negative 2x cubed graph. So questions would look like this. Find the critical numbers and then identify them as local max or min, or neither. So f at x is equal to x squared over x cubed minus 1. So in order to work this one out, we do need to find the first derivative. Before we do that, however, we should note any restrictions on the graph, because if the graph doesn't exist at a certain point, then we do not take the derivative of it at that point. So x cubed minus 1 cannot equal 0. So x cubed cannot equal 1. So x cannot equal 1. So we need to be aware of that. And if we're going to differentiate this, we want to use the quotient rule, or I will at least. So u is equal to x squared. U prime is therefore equal to 2x. V is equal to x cubed minus 1. So V prime is equal to 3x squared. Therefore, y prime is equal to u prime v minus u v prime over v squared. So y prime will be equal to u prime is 2x times v, which is x cubed minus 1, minus u, which is x squared, times v prime, which is 3x squared. And then all this over top of v squared, which is x cubed minus 1 squared. Then y prime is equal to, we clean up that numerator and we'll get 2x to the 4 minus 2x minus 3x to the 4. And then this all over top of x cubed minus 1 squared. Y prime is equal to, subtract the x4 terms, and we should get that y prime is equal to negative 1, or negative x to the 4, minus 2x, it appears to be, all over top of x cubed minus 1 to the 2. Now, going on a little bit, if we factor that numerator out, by taking a negative x out. Now we could take a positive x, it really doesn't matter, but it's got the x should be removed. So factor these completely and you'll get x cubed plus 2. And then this is all over top of x cubed minus 1 squared. So we now, I'll bring up, get a little more space to work. We now do first derivative analysis on this function. Oops. So oops, try not to do that. My hand's a little shaky here today, looks like. F prime at x is equal to negative x cubed plus 2. So it's a bit of a nasty looking one. All over that denominator again, x cubed minus 1 squared. And to get the critical numbers, we have to be very careful, because critical numbers occur where f prime at x is equal to 0. So we first off begin by setting this derivative to 0. So negative x and then x cubed plus 2 all over top of x cubed minus 1 squared. Now recall that when you're trying to set this rational expression to 0, we care only about the numerator. So 0 is equal to negative x times x cubed plus 2. So we solve this, and we'll get negative x is equal to 0. We'll also get x cubed plus 2 is equal to 0. So our two critical numbers will divide by the negative, will be x is equal to 0, and x cubed is equal to negative 2. Don't bail out on that one, because x, we can take the cube root of a negative number, just not an even root. So the cube root of negative 2. Then we also have to be aware that critical numbers occur where f prime at x doesn't exist. So never forget this, particularly when you're dealing with rational expressions that have a denominator. And it won't exist where x cubed minus 1 squared equals to 0. So where the denominator is equal to 0 is where we will start. Now it's true that other points could be found where the derivative doesn't exist, but typically it's on the denominator. And we take the square root of both sides, we get x cubed minus 1. I don't think I wrote that denominator right, though, did I? Nope, I guess I did. All the fuss, remembering what the question was, is equal to 0. So yeah, we're okay. X cubed is equal to 1. So here's what we get, x equal to 1. But note, x equal 1 doesn't exist on y equal f at x. In other words, f at 1 doesn't exist. So therefore, x equal 1 is not a critical number. So that's important. Even though we found a value that could look like it was going to be a critical number, you always have to go back to the original function. And if that point doesn't exist on the original function, then it's not a critical number, because a critical number must actually be on the function itself. Makes sense. And now we do the interval analysis on this one. It's kind of a messy one. So I'm going to get some more space in the next screen. Now, I do have this graph up here which is going to interfere. I was going to graph it, and I don't think I will now. But we set up our number lines, and with care, I didn't actually draw them out for you this time, unfortunately, but we have the factor negative x, we have the factor x cubed plus 2, and then we have the factor x cubed minus 1 to the exponent of 2. And all this together is our derivative. And then we note the critical numbers on this. So it's the same process as we've always done. The critical number for negative x is 0. We've got that established. We also have for x cubed plus 2, it's the cube root of negative 2. So the cube root of negative 2. So you probably want to work that value out so that you can know what numbers to pick. So take the cube root of negative 1. It's about 1.26. So about, or negative 1.26. So we know where to go with this one. Now regarding the x cubed minus 1, we also want to note 1 because that point doesn't exist on the graph, but we need to be aware if anything's happening there. Don't know why I put that graph up. So for negative x, substitute values in, and if you pick numbers bigger than 0, say 1, the function will be negative forever and positive to the left. So be careful with that negative sign because, of course, that reverses everything. X cubed plus 2, if you pick a number bigger than the cube root of negative 2, say 0, it's going to give you a positive value to the right. And a negative value to the left. X cubed minus 1 squared, well, pick a number bigger than 1 for that. It's going to, or less than 1. It's going to be positive everywhere when you square that number. So that didn't have any effect on any of the signs. And then we note that the derivative is negative in that first interval. It's positive in the next interval, negative, and then negative. So it is, because the derivative is negative, goes down, goes up, goes down, and goes down. So from here we can tell what critical numbers are producing mins or max. So we would then say there is a local minimum at x equal cube root of negative 2. So that's where the graph, the derivative changes from negative to positive. So basically by inspection we can tell. And then there's a local maximum at x equals 0. Because there the derivative changes from positive to negative. And x equal 1 does not produce a min or a max, which makes sense because that doesn't exist on the graph, so we wouldn't expect it to be a turning point. So that's the procedure that we have to go through with each of these. So you begin to get an idea that this is not that quick. And in fact, it is not that quick. And you also will be doing second derivative analysis on these to further complicate things. I'm not going to bother graphing this one because it probably isn't worth our time to do so, but feel free to graph it and see if those numbers seem reasonable. Now this one, y is equal to x to the 5/3 minus x to the 2/3. So let's go through this, and it works out nicely. Be really careful with this because when we're trying to find restrictions on this, when people see that they're taking the root, which is what's happening with those rational exponents, they tend to think, I cannot take the square root of a negative. So they think they have a restriction on it. And now that would be true if you're taking a square root. But in this case, there's no restrictions on the domain at all. You can plug in, this is the cube root of x, and you can take the cube root of negative numbers. So the domain is going to be all real numbers. So that does matter. When we take the derivative, dy dx, doesn't matter which notation you use. I will eventually write this as f prime, just because that's the way they lend themselves to that sort of substitution. So we get 5/3 x to the 2/3 minus 2/3 x to the negative 1/3. And then dy dx is equal to 5/3 x to the 2/3 minus 2/3 over 3x to the 1/3. Now you have choices with this, but I really advise you to express this with a common denominator, and then I'll write this as f prime at x. It makes the analysis much easier, and we saw this in a question fairly recently. So our common denominator would be 3x to the 1/3, and then the 2 will stay the same. But to make this one with a denominator of x to the 1/3, we have to multiply top and bottom by x to the 1/3. And in doing so, we would get 5 x to the 2/3 times x to the 1/3. If you add the exponents, it's just x to the 3/3, which is x to the 1. And that changes things, because now we get a nice clean numerator. And we again go after our critical numbers. And we really, with extreme care, we set it equal to 0. And we have a numerator, we have a denominator. That's exactly the way we want it. It makes the analysis very easy. And where this function will be equal to 0 will be found where the numerator is equal to 0. So 0 is equal to 5x minus 2. So I'll solve that quickly. 2 over 5 is equal to x. Now the other critical number is where f prime at x, or potential critical numbers, doesn't exist. So this will be where the denominator is equal to 0. So 3x to the 1/3 equals 0. Divide by 3, x to the 1/3 is equal to 0. And then when you take cube each side, you'll get x is equal to 0. Now pay attention to the original graph, or original function, and you'll see that that point actually does exist. So it is a critical number. So we have two critical numbers, 0 and 2/5. Now, I'm not going to graph this one. I don't know why I didn't bother with some of these graphs, because they're good graphs. But in any event, if you graph it on your own, you'll get a good look at it. We would expect there to be a cusp at x equals 0, which is normally what happens. You get sort of a corner at that point. So I'm going to get some space and write this thing out again, and do the analysis. F prime at x is equal to 5x minus 2 over 3x to the 1/3. So we draw out our number line. And our first factor is 5x minus 2. Then 3x to the 1/3. And then f prime at x. And then for 5x minus 2, we've already noted that the critical number is 2/5. And then for 3x to the 1/3, the critical number is 0. So now we just do the analysis, and from this we will find out what our local min, local maxes are. So 5x plus 2 is pretty conventional. If we pick an x value larger, it'll be positive, and then negative to the left. 3x to the 1/3, pick an x value bigger than 0, say 1, and it will be positive. And then negative to the left. So therefore the first derivative is positive in the first interval, negative, then positive. So I'll indicate that with the arrow up, arrow down, arrow up. So therefore, we can see that we have a local max at x equals 0. Now keep in mind that is not the local max, because that would be the y-coordinate. We'd have to plug that into the original, which we'll do soon. And then a local min at x equal 2/5. So try graphing it just to get a sense of what's going on. I'm not going to, but it would be x to the exponent. Make sure you graph the original of 5 divided by 3 minus x to the exponent of 2 divided by 3. and it should verify what we have. So you're getting good information based on these critical numbers. Now the next one, we're actually going to sketch this one. So y is equal to 3x minus 2 to the 2/3 and plus 1. So we do the same thing that we have always been doing, and we note first off that the domain, there are no restrictions on it. Once again, we've got the cube root, and that's okay. We can take the cube root of any number we want. So when we get the derivative, f prime at x, we use the chain rule on this. So 3 times 2/3 will give us 2 times x minus 2, subtract 3 over 3 from 2/3, and you have negative 1/3, and then plus 0, and then multiplied by the derivative of the inner, of course. So f prime at x is equal to 2 over x minus 2 to the 1/3. So that actually wasn't too difficult to differentiate. So now we find the critical numbers. Please pause me at any time and work through this question on your own. So f prime at x equals 0, and we set this function to 0, and we will note that it is impossible for this to be 0. 2 will never be equal to 0. So f prime at x cannot equal 0. So no critical number found. Then go on to the next part. Where does f prime at x not exist? So this would be where the denominator is equal to 0. So 0 is equal to x minus 2 to the 1/3. Cube both sides to get rid of the 1/3, and you'll get 0 is equal to x minus 2. So x is equal to 2. So our only critical number is x equal 2. So now I'm going to, on the same page, I'll do my interval analysis. Don't know why I didn't draw a number line for this one. Remember that. So put in your factor of 2. Now some of you are thinking, why do I put that 2 in there? No good reason, because it's not going to affect the sign, just force of habit. And then here's f prime at x. And the only critical number we have is at 2. So 2 is positive everywhere if you included it. And then x minus 2 to the 1/3, if you pick a number bigger than 2, pick a number like 10. 10 minus 2 is 8. Cube root of 8 is 2. It's going to be positive to the right and negative to the left. So our first derivative is negative there, positive there. So it tells me the graph is going down and then it's going up. So a local min at x equal 2. Moreover, because we were asked to sketch this, we now need to find out what the corresponding y value is. So f at 2, you go into the original function, is 3 times 2 minus 2 to the 2/3 plus 1. So f at 2 is equal to 3 times 0 to the 2 cubed plus 1. So f at 2 is equal to 1. So therefore, there is actually a local min is 1 at x equal 2. Now I'm going to graph this one, or I'll bring up the graph. You've actually got it on your notes if you printed that off. And we will see a distinctive type of graph emerge. So that's what we get, is we do have this cusp. At 2 comma 1. So once again, we're able to get a lot of information from these first derivatives. Now let's take a look at the next two graphs, or the next two questions, which all require similar sorts of things. F of x is equal to x squared over 1 minus x. Now this graph is fairly routine looking. We note that the domain 1 minus x cannot be equal to 0, so x cannot be equal to 1. So that may come into play later on. And then we get the first derivative, and we're going to have to use the, well, we probably will use the quotient rule. So u is equal to x squared, so u prime is equal to 2x. V is equal to 1 minus x, so v prime is equal to negative 1. So therefore, y prime is equal to u prime v minus u v prime all over v squared. So y prime is equal to 2x times v, 1 minus x, minus u, which is x squared, times v prime, which is negative 1, all over v squared, so 1 minus x to the 2. So y prime is equal to 2x minus 2x squared plus x squared, watch your signs, all over 1 minus x to the 2. And y prime is therefore equal to, this is a minus in between, so we'll get 2x minus x squared over 1 minus x to the 2. Take it right to the top. F prime at x will be equal to, factor out an x, and you'll get 2 minus x all over this 1 minus x to the 2. So critical numbers, we go after them. Set the function equal to 0. So 0 is equal to x, bracket 2 minus x. So x equals 0, or x is equal to 2 when you set 2 minus x equals 0. F prime at x doesn't exist. Well, 1 minus x squared equals 0. Well, you will get 1 minus x is 0. You will get x equal 1, but not a critical number. Remember, f at 1 doesn't exist. So, when we do our analysis, I'm just going to sneak it in this page. We have one factor of x. We have another factor of 2 minus x. And we have the other factor of 1 minus x to the 2. And then that would altogether give us our first derivative. A little tight for space, but we should be okay. So there's 0, the first critical number. Then 2 is the other critical number. But be aware, too, that the value of 1 is worth including, even though we don't expect it to produce a sign change. So some people don't put it in because of that. But it is helpful just as a reminder, in my mind, of that something is going on at that point. So x0 will be positive to the right of 0, then negative. 2 minus x will change signs, but be careful, because if you picked a number bigger than 2, it'll be negative to the right, positive to the left, so it's been reversed. and then 1 minus x squared is positive everywhere. So this derivative is negative, it's positive, it's positive, it's negative. So it's going down, it's going up, it's going up, it's going down. So I'm going to just sneak this in at the bottom. Local min at x equals 0. And then a local max, hopefully you can see this on your screen, at x equal 2. So I will bring up the screen for the graph, and you can actually see this one. Now it's a little tough to recognize the mins and the max based on this, but there's our asymptote at 1. But and as far as getting the values, I guess we should find them. So for x equal f at 0, if we plugged in 0 to the original function, we will get 0 squared over 1 minus 0. So f at 0 is equal to 0. So therefore the local min of 0 at x equals 0. And then when you find f at 2, 2 squared over 1 minus 2, f at 2 will be equal to 4 over negative 1. So f at 2 is equal to negative 4. So therefore a local max of negative 4 at x equal 2. So that is somewhat verified by the graph. It's pretty tough to recognize in a case like this what the max or min is, but that is correct. And then the asymptote x equal 1. Now we've been going on a long time here, so I'm just going to quickly go through the next graph and the next function leading to the graph, just because this is a variation that might interest you. So for the square root of x plus 3, x has to be greater than or equal to negative 3. So x plus 3 has to be greater than or equal to 0. So when we do differentiate it, f at x is equal to x plus 3 to the 1/2. So the first derivative, f prime at x, is equal to 1/2 times x plus 3. Subtract 1 is negative 1/2 times the derivative of the inner, which is 1. So f prime at x, if we put it all together, is equal to 1 over 2, and then square root of x plus 3. So that's interesting. And if we take a look at what we have for critical numbers, we set this f prime at x equals 0. So 0 is equal to 1 over 2 root x plus 3. They're none. The critical number for this one, you're not going to get, this cannot be equal to 0 based on that number on top. So then we take a look at where f prime at x doesn't exist. So this is interesting as well. So this would be where 2 bracket x plus 3 is equal to 0. So the root of x plus 3 equal to 0. Square all this, x plus 3 is equal to 0. So x is equal to negative 3. So according to that, we do get a critical number at x is equal to negative 3. So let's take a look at what's going on here. On our number line, you're already probably thinking something doesn't seem right. I'll put the 1 there even though it's not necessary. And then I'll put the 2 there, even though it's not really necessary, and then the root of x plus 3. That's just a reminder to make sure that you do not forget factors, and if you do not put them there, make sure that just leave the positive ones out. So 1's positive everywhere. It doesn't do anything for us. 2 is positive everywhere. And then x plus 3, well, if you set that equal to 0, we do have the value of negative 3. But the problem is with this graph is that it doesn't exist to the left of negative 3. So there can be no sign change, and this is always positive. So this function is always going to be, or the derivative will always be positive. And this means that there is no local min or max. X at x equal negative 3. There would have to be a sign change for it, and that's really the start of the graph, x equal negative 3. And if you take a look at the graph that results from it, we can see that the graph is always increasing. It does not count as a local minimum. It would, on the other hand, be within a certain interval there would be considered an absolute minimum. So I'm going to stop right there. That's been going on for a long time, but there's lots of information in that. And then soon we'll be going back a little bit almost to do absolute max and min, but this is the idea that we'll be working with. And then on to second derivative analysis. So thank you for your time.